Change this. Cool. Okay. Hello, everyone. It is a great pleasure to introduce our colloquium speaker for today, Dr. Joshua Wiley, Senior Research Fellow in the School of Psychological Sciences and the Turner Institute for Brain and Mental Health at Monash University. He is a leading researcher in behavior medicine, widely respected for his work at the intersection of sleep, psychological process, and health. His research bridged both basic science, exploring the day-by-day longitudinal dynamics of sleep, stress, and coping, and intervention science, in which he develops and tests approaches designed to modify their mechanism for improved health outcomes. So today, Dr. Wiley will represent sleep as part of the 24-hour day method and application in oncology. Please join me in welcoming Dr. Joshua Wiley to this online stage.
Thank you so much, Professor Kim. I really appreciate you inviting me, and thank you to everybody for being here and taking the time to listen. Mm-hmm. Just a couple of notes. If you have questions along the way, please feel free to interrupt or to post some comments in the chat. And I think there's some time for question and answer afterwards as well. Okay, so I feel like I should give some caveat maybe at the start. So I'm going to share some of the methods that we have been developing and been using, but I am not a mathematician. So I feel like talking in front of all of you, I probably will sound quite dumb. But hopefully there's some stuff that you can learn off of some of these methods, and maybe you can also teach me some things about them. And then I'll also talk about how we have applied these to different contexts in daily life, and talk about some of our interventions for people with cancer, and then directions for the future where I hope to bring them together. Okay, so just a little bit of an overview. I want to start with talking a little bit about sleep and activity profiles in cancer to set the stage. And then I will talk about the compositional data analysis with some introduction to the method and an application. Talk about our interventions, which kind of leads into then a multi-level compositional data analysis, and then discuss some limitations and next steps. So just to sort of start things off, sleep and daytime physical activity are not independent. They're part of a fixed 24-hour daily budget. So we all have 24 hours in a day, right? We don't get more hours in a day, no matter how much we wish we can. Mm-hmm. So this first study was led by my PhD student, and she's now a postdoc, Flora Le. And she used this study using the accelerometer data from the UK Biobank. Very little bit of background. Probably many of you are familiar with the Biobank. I think a lot of papers published on it, but it's a very large data set from the United Kingdom. The overall data set, I think, has around 500,000 people, but there's around 100,000 who have 7 days of accelerometer measured. And then there's some machine learning models that have been used to assess 24-hour behaviors, so that's sleep and activity, based on the accelerometry data. And the participants are typically middle-aged, so they're around like a 40 to 80 usually, but the average here you can see is a 62, about even split of men and women, and trying to broadly be representative of the United Kingdom population. So we use the data from linked health records and the ICD-10 codes to classify whether people were cancer survivors. So that is, they had any diagnosis of any type of cancer in the past prior to the accelerometry, whether they had no cancer and no other chronic conditions at the time of accelerometry, which was about 13,000 adults. It turns out most people have a chronic condition. Mm-hmm. Or whether they had some chronic health condition, so that can be like high blood pressure or cardiovascular diseases, or kidney disease, any other kind of disease. We don't really care. but any other chronic health disease that was not cancer at the time of accelerometry. And that was about 67,500 participants.
Mm-hmm.
This paper not published yet, but it's under review. And so we look at these things. And so the machine learning models that were used to classify these data categorized the 24-hour period into four domains. So time spent in sedentary behavior. So that's sitting, like probably all of us are doing right now. So that's on the top right. Mm-hmm. Time spent in light physical activity. That could be doing chores around the house, slowly walking, things like that. Mm-hmm. Time spent in moderate to vigorous activity. And this is usually like a brisk walk or running, doing weights, playing more active sports. And then they call the sleep period, which is basically akin to sort of time in bed. So it's not strictly being in the state of sleep, but really the time from kind of when you would go to bed to when you would get out of bed. And so what we did is we just quantified all of these based on the healthy adults. And this is kind of shown here, their average down in this dashed line. On the x-axis, we have the minutes. We also show the minutes and the confidence intervals plus the number of participants contributing to each on the graphs. So what you see really clearly is that people with cancer have quite a bit less, about 22 minutes less, about 7 minutes less MVPA per day. These is per day estimates. So we take the 7 days, we average it though. So about 7 minutes less MVPA than healthy adults. They are not significantly different from people with other chronic health conditions when we look at cancer overall. They spend more time in sedentary behavior, also less time in light activity, and a greater amount of time in the sleep period. And we present all of these together. So going back to that, we all have 24 hours in a day. If somebody spends less time in moderate to vigorous physical activity, or I will say MVPA, they have to spend that time somewhere else then. And so looking at all of these together, then you can see they spend less time there, they spend less time in light activity, but they have to counter that somewhere. And so they are spending more time in sedentary, sitting, and they spend more time in bed, basically, in the sleep period. We also separated these results down by how long ago they were diagnosed with cancer. And so the thinking being, if you have been diagnosed with cancer a very long time ago, you may have be doing quite well now, be healthy, have recovered, and so you're not really as impacted by it. And conversely, if you're in the first year after a cancer diagnosis, you're probably much closer to the treatment or the medical treatments for cancer, which can be quite disruptive to sleep and health. And so there we do see that pattern, at least for this sort of 1 year. When they're within the first year since diagnosis, there's the greatest reduction in moderate to vigorous activity, in light physical activity, the greatest increase in counter and to sedentary behavior, and the greatest increase in the sleep period. And that diminishes a little bit as people move further from diagnosis. So that gives us a little bit of a sense of, of sort of cancer overall. And now there's a lot of variation across this. So that combine all cancers together, like cancer is one homogeneous disease, but it's not actually so homogeneous of a disease. And so fortunately, because the biobank is quite large, there's sufficient numbers, I think, to look at to different types of cancers. And so these are the same sorts of plots, but now we have broken down the cancer by the different category of cancers, so whether it's in the skin or the prostate, melanoma, etc. And these are the MVPA data, and you see there's quite some variation. The best cancer for MVPA is the skin cancer, and they get about 24 minutes of MVPA a day. The worst cancer is the lung cancer, who only get about 11 minutes of MVPA per day. And the other thing that we did in looking at this is that it looked quite a bit like it was ranked from sort of the cancers with the best prognosis to some of the cancers with some of the worst prognosis. So we know that people have a much shorter life expectancy after lung cancer, for example. And so just we pulled from some other data the 5-year relative survival rates for each of these cancers. There's a couple, the other category, which because it is captures a bunch of rare cancers, we can't get data on easily. Um, and we cannot find good data on non-melanoma skin cancer. But you can see for the other cancers that we're able to get data on the 5-year survival rates, which are listed as a percentage. So 100% would basically be a relative survival equivalent to someone who didn't have the cancer diagnosis. And as it goes down, it's like a multiplier of your 5-year survival compared to somebody without the cancer. And so what you see more or less declining as you move sort of down this graph, it's not a perfect one-to-one correlation, but it's quite related, where these kind of cancers with the much higher survival rates have a lot better physical activity, and the cancers with the much worse survival rates tended to have a lot worse physical activity. So just kind of a nice link up there between these factors. Now, this linked up very nicely for moderate to vigorous physical activity. When we look at, too far. When we look at the sleep period, it's actually kind of a mess. So there's not really any clear pattern between the survival rate and the sleep period. Part of this, I think, may have to do with the data that we have. So we work with a group from Oxford University who do a lot of work with the UK Biobank, but I think they were more interested in physical activity than they were interested in sleep. And the data they have released for this then from those machine learning algorithms has this kind of sleep period that incorporates, both actual sleep at night, but also if they're spending a lot of time in bed, perhaps because they're tired, even if they are not actually sleeping, that gets counted into this. And so that may partly explain why there's not too consistent of a relationship here. And somewhat interestingly, and perhaps counterintuitively, every cancer type is spending more time in this sleep period compared to healthy adults, which again, perhaps doesn't make sense from an actual sleep perspective. But if you think about they're tired, they're unwell, and they're spending the extra time in bed, it can make some sense.
Mm-hmm.
Okay, so that's just a little bit of setting the stage. And I guess it points to a little bit some of the disruptions to people's 24-hour day when they have cancer, which we'll come back to when I talk about interventions and why we try to do sleep interventions, particularly with people with cancer. But before I go into that, I want to set up some of the method background, which is this compositional data analysis. So compositional data is when you have plots that carry relative information. That happens when they're constrained to a constant sum. So that can be like a 24-hour time use. It can be other things as well. So in geology, for example, you might look at the soil composition, how many minerals or different types of rocks or things like that. I don't know, I'm not a geologist. Make up a sample. In some other cases of biology, I know people will have like some tissue samples or some biologic samples, blood or something like that, and you might look at the percentage or the proportion of different cell types. And so these things are relative information because they always have to add up to the whole. So, in a 24 hours of time, no matter what you spend, it has to add up to 24 hours within a day. If you have a fixed quantity of tissue or a fixed, blood or something like that, the different cell types have to add up to 100%. And some of the implications of this is that if you don't use analyses that respect that, and so they call it like the simplex geometry, if you use sort of the ordinary Euclidean space, right, you can get predictions that go outside of that. So you could end up saying like, for people who have cancer or something, if you don't use this, we predict that they spend 13 hours in bed and 13 hours sitting and 2 hours in light activity. And so it will end up summing beyond 24 hours. So it can become sort of impossible. I think you're probably all very smart people, so I don't know I need to show you this, but anyway, I show you just a little demonstration of what this could look like. So can you still see my screen?
Yes, very well.
Okay.
Wow.
Okay, so here is like some hypothetical time use, right? TST for total sleep time, wake, SP for sedentary behavior, LPA for light activity, MBPA for this. Mm-hmm. And so if everything is sort of not constrained, if we say somebody like, okay, spend another hour in sleep, other categories have to shift, right? They have to get smaller. If we spend more and more time in sleep, all the other categories must shrink down. Or you can imagine, okay, what if somebody isn't going to shift some things, like if
Mhm.
somebody doesn't move their MVPA, for example,
Mhm.
and they're not going to change how long they spend awake at night. It still take them some time to fall asleep, let's say, no matter what. And we ask them to increase their sleep. Then in that case, it will have to be countered by sedentary behavior and light activity. If you fix some of the things. So these always have to sum. And so there's a trade-off. And one of the things I think is quite interesting about this conceptually, let's see if I can go back to my slides. Yeah, is a lot of times we study these things individually, right? And so in this sleep research, especially as we head into the intervention space, and I'll talk about this a little bit later when I get there, it's common to say, okay, you should be getting 7 to 9 hours of sleep, right? But we very rarely tell people how they should get that. So if somebody comes in front of you and they say, okay, I sleep 6 hours a night, and you say, okay, for your good health, you should sleep 7 to 9 hours, we will make that recommendation. We say basically spend more time on sleep, but we don't say what they should give up to do that. And you maybe have different outcomes. For example, if somebody spends 1 more hour in sleep at the expense of MVPA, or they spend 1 more hour in sleep at the expense of sedentary behavior, then maybe for their health, actually, it's quite different outcomes. And so compositional data analysis also enables us to start looking at those things. Okay, so a little bit of math, and again, I'm not a mathematician, so please don't be too harsh on me, but I do my best to explain.
Yeah.
So total, we consider a D-part composition. So that can be arbitrary numbers. A lot of times we work with 5, but it can be any number of components. So we have some vector X, which comprises these different components. For example, the sedentary, light, MVPA, sleep, wake, for example, right? And it's a composition when the sum of these components is equal to some fixed constant. And for each component is greater than 0. So you cannot spend less than 0 time in sedentary behavior, for example. You can spend 0 hours in it, but you cannot spend less than that, right? So it is strictly positive for all components. And then we commonly define this closure operator to basically take I think actually the C as a typo, it should be a K. But anyway, where it normalizes X so that all of these components together will sum to the same quantity. And this is helpful for several reasons. But we'll also use this. So sometimes when I talk about, say, the 24-hour day, there's different ways to define it. Now, obviously, if we hold a precise 24-hour day, it will never vary. But then also sometimes it does vary a little bit. So for example, if we measure people from wake to wake, rather than from, say, midnight to midnight, then one day I wake up at 6 a.m., another day I wake up at 7 a.m. And so, one day I have like a 25-hour day, another I have like a 23-hour day. And so you can use the closure operator to norm that. And then the other piece that gets used a lot is you can think about perturbing a composition. And so here I show that with X and X prime. And this is sort of analogous to addition or subtraction in Euclidean space, but in the compositional space, we use basically a multiplication of it, essentially. So you have a sort of one composition and you modify that into another composition. Okay. Now, you kind of have two ways. I have this? No, I don't have it. You kind of have two ways that you can broadly analyze these. And I don't know if I talk about this more later, but you either work with the composition directly. So we call it here on the simplex space, right? So this space has a D dimensions for every component of your composition, right? And if you work with that, then your analysis method needs to accommodate that. And so you might use a distribution that accounts for that, such as the Dirichlet distribution that can then work directly on the simplex space. And then some of us maybe are not quite that smart or a little bit lazy. And so you can think about some other ways of doing it. And if we could somehow take the simplex space data and transform it to work with our usual statistical analyses or data methods, then it's a little bit more convenient. And one of the ways that you can do that is the isometric log ratio or ILR transformation. And this maps the simplex space into the real space, but now with d-1 dimensions. Because since a composition has to sum to a constant, once you know d-1 of the d components, you can predict the last one. It has to fill in whatever the gap is. So they're not fully independent. With a transformation like that, then you are able to sort of analyze it directly. Standard statistical methods can get applied. So now we can then reapply things like regression, linear regression, or methods like that to it, to these ILR transformed values. And the way that these standardly get defined, I should put some citations in here, but I'm sorry, I can send you afterwards, is they're normally these normalized log ratios of geometric means. So I just put a little definition of it down here. The geometric mean, so here is your kind of the key part. You have basically some numerator and some denominator. What you choose to put into each of those is up to you. There's different ways that can be defined, and I think I'll talk about that in a second. But essentially, if you have 5 components, you might first contrast, for example, sleep and wake versus all the physical activities. In that case, the numerator would be the sleep and wake. The denominator would be all the physical activities. And then we take the log of that ratio, the natural log, and then there's this normalizing constant based on the sizes of the partitions that went into each of that. Don't know how well that's explained, but I think there's an example make it maybe a little bit more concrete here. So we can define these ILR coordinates really any way that we want. But this is one people commonly use. They call sequential binary partition. So I'm just going to work here, assuming that we have this 5-part composition. Sleep duration, total sleep time, or TST. Wake during the sleep period. So that's like when you try to go to bed, but you're lying there awake, struggling to fall asleep. Or maybe you've fallen asleep, but now it's 1 a.m. and you wake up, your cat wakes you up, and now you are awake and you spend half an hour awake. So those things would go into wake. We have MVPA, which I talked about before. We have light physical activity, sedentary behavior. So we have these 5 parts. For a D-part composition, the ILR coordinates will always have 5 minus 1. Right? You have a 1 fewer than the simplex space. So we have these 4 coordinates defined here on the rows. And this kind of coding scheme here, a +1 means we put it into the numerator, a -1 means we put it into the denominator, and a 0 means it wasn't considered. So you can define these in different ways, but here, for example, the first component, the first coordinate, we define as basically sleep period, actual sleep duration plus wake during the sleep period versus all the activity. The second component is a contrast just between sleep and wake during the sleep period. Second component contrasts MVPA versus the remaining activities. The last component, light activity versus sedentary behavior, basically. And the normalizing constant based on the number of components that went into it from this sort of formula. And so that then is our transformation at this point. If you apply this to the raw data, then you would get these sort of 4 new variables, which are the ILR coordinates, and to which we can treat as sort of independent variables. And of course, you can back transform ILR coordinates back to the original scale so that rather than try to interpret this variable on its own, which is maybe very confusing variable to try to interpret to somebody. What does a 1-point change on that mean if you're using regression, or you have some graph, you don't want your x-axis to be some uninterpretable numbers. And so we can back transform the results after this. So we can transform, apply an analysis method designed for real data. And then when we are done, as kind of common in regression with like link functions or things like that, we can back transform the data away from the coordinates into the original simplex space so that we can talk about minutes or hours or things like that. So this is a paper we published a few years ago, and we looked at these composition analysis of these data along with daily affect. And it came from an ecological momentary assessment study that I ran, where we had about 360 adults, mostly female. These were young adults. We collected them. Primarily, they were university students. They were measured for 7 to 15 days with an average of about 10. And for all those days, they wore accelerometers. They were used to track their sleep and physical activity. And then they used an app to report on emotions they were experiencing, like happy, sad, things like that, that we use to calculate affect each day. And so I won't go through all these numbers, but just some descriptives, how much time and hours they spent in the different activities after we score the data. So pretty healthy, pretty normal people, get about 7 hours of sleep, spend a good amount of time per day in MVPA, spend some time, about an hour awake, trying to fall asleep or awake each night. Again, these are fairly typical data for sleep and physical activity and young adults. And we had we pulled the data from 3 studies, is why I have 3 columns here. And these are just the study names, but I think the names aren't so important for today. And so then we can look at the results on this. And after we do those transformations, so we get those ILR coordinates, but as I mentioned, it's not very convenient to interpret results that way. And so we do what is called like substitution analysis, but it's basically just prediction. You can generate how you predict your outcome. So in this case, we put all the composition in as predictors. We look at affect as an outcome. So high arousal, negative affect. That's things like anxiety or worry. And we can then ask, after we build a model, is this just a basic linear regression? It's not complicated. But then you can put in different predictions. So we can increase, for example, time awake in bed at the expense of sleep duration, and then generate predictions at one point, and then we increase awake in bed, reduce sleep duration, generate another set of predictions, take the difference between those 2 predictions, and that tells you how the model predicts high arousal negative affect will change when you increase time awake in bed at the expense of sleep duration. And you can do that for every pairwise combination, or of course you could do it for multiple behaviors at a time. So you don't have to do it pairwise, but I think it's a little bit easier to think about it pairwise. What you see here in these results is that if participants spent more time awake in bed at the expense of any other behavior, so it doesn't matter what is reduced to compensate for that time awake in bed, they're predicted to have a more high arousal negative affect, so more kind of anxiety or worries. And we also did a kind of continuous, varied the number of minutes that we substitute in or out from about -45 to about +45. And you can see the curves predicted here on this graph as well. And you see, regardless of what it's getting substituted for, it didn't really actually make much difference, which I guess is the nature of science sometimes, even if it's a little disappointing. We have this possibility to see, does it matter what you substitute? And then anyway, the data tells you, no, it doesn't matter. No matter what you replace it with, it's worse for you to be awake overnight, and it doesn't really matter whether you are giving up sleep to do that or giving up sedentary behavior. You are just more anxious no matter what it is. Mm-hmm. But still, it's a little bit interesting to be able to take that approach. We did the same thing with high arousal positive affect. And this is like feeling things like enthusiastic or interested. It's the sort of emotions that you might get when you're working on some hard problem and then you solve it and you're feeling kind of engaged or happy with that. It's those sorts of things. And here we find that spending more time in MVPA at the expense of light or sedentary behavior or sleep is associated with more of those kind of emotions. So this just kind of a little bit of an illustration of how these kind of compositional data analysis can get applied to real data. Now, what I should say in this is, even though we had multiple days of data in these studies, at this time in 2022, we had only started using CODA, or compositional data analysis, and not many people had applied it to repeated measures or multiple days of data. And so for all the analyses that I'm showing you here, we had just averaged it. So we took the average sleep, the average activity, the average emotions across all the days of our studies. So that is kind of all that's here. And I'll talk a little bit later about extensions to this. Let's see what else. Oh, last thing, maybe just a little comment. I don't know how much this applies in mathematics, but at least in statistics, we worry a lot about, or think a lot about, how we calculate confidence intervals or uncertainty intervals. And so for these kind of substitution analyses, there are, differences in predictions. So you generate predictions given one composition, then you create a different composition where you've substituted things, you generate a new prediction. You take the difference between those two predictions. To generate confidence intervals for those, like shown in these tables, usually people will either use bootstrapping or they'll use Bayesian analyses where you can sample the posteriors, get a predicted posterior, and then just take the difference in those two posteriors and generate credible intervals off of those. So I can talk more about Bayesian methods later as well if you are interested.
Mm-hmm.
Okay, so now I want to shift a little bit and talk about some interventions for sleep and then sort of carry forward from there. So this was work led by one of my former PhD students, Helena Bean, shown here.
Uh-huh.
And we published a couple of years ago in Sleep.
Uh-huh.
And this was a combination of cognitive behavior therapy for insomnia, which is basically trying to change how people think about sleep and also, very importantly, change some of their behaviors around sleep. So, for example, we will try to have people use a routine bedtime and wake time. We will work with people to try to get them not to go to bed until they're actually sleepy. So, especially with sleep problems, sometimes people, even they're not very sleepy. Like, for example, if you don't sleep well tonight, and so you're tired tomorrow, a very natural thing might be, I'm going to go to bed extra early, right? So I normally go to bed at 10 p.m., but because I'm so tired today, I go to bed at 8 p.m. But the problem with that then is your sleep is not aligned with your circadian rhythm. Your body clock is not giving you the right kind of sleep signal. It's more difficult to fall asleep, and this can lead people to have more problems. So, for example, another thing that we do in the CBT is try to make sure that even if people are a little bit tired, that we usually ask them not to go to sleep before their usual bedtime. I think there's quite a few circadian researchers here, so probably nothing very new there. And so, yeah, that's the kind of the cognitive behavior therapy. The other part of this is that it was bright light enhanced, and I should have brought a pair with me, but we use bright light glasses. So we use luminette glasses. They basically, you can wear them over your regular glasses, but they just have LED lights, and they give a blue enriched, about 464 nanometer wavelength is the peak light to deliver to the eyes. And we had most people wear these for about 20 minutes each morning in the intervention condition. And the control condition was just basically treatment as usual.
Mm-hmm.
And this was done in women with breast cancer. And we picked particularly while they're receiving the chemotherapy. And so there's some literature out there that even though breast cancer is not the most worst prognosis cancer, that women with breast cancer have quite a bit of trouble with sleep, quite a bit of complaints about sleep. And we also know that during the chemotherapy, the drugs from that and the treatment for it is quite disruptive to sleep. And so we thought picking that particular treatment and trying to actually intervene while they are undergoing the chemotherapy may be interesting, because if that's when they have a lot of trouble with sleep, maybe we can address it early rather than wait for them, months afterwards. Okay, so I think I have told you a little bit about this. So we randomized them to either the intervention group, which is the cognitive behavior therapy plus light. This is a very brief intervention. So we do a single in-person session, then one phone call, and we give them the rest of the content by emails. And then they use the light glasses each day, but they just do that at home. We give it to them and they can wear it at home. Control group, treatment as usual. We randomized 101 women across the different groups. And our main outcomes were sleep-related, but actually collected via surveys or self-report. So not the objective data yet, although we did collect that as well. So we measure the insomnia symptoms. So this is with the insomnia severity index. Women basically self-report some different questions like, how much difficulty do you have falling asleep? How much difficulty do you have staying asleep? Is it a problem? Is your sleep a problem for you during the day? For example, like you might be tired. And so we measured that. And the blue group in blue circles are the intervention group. The gold triangles are the control group. And so they start off, and in the intervention group, we have significantly greater improvements in insomnia symptoms up through the post-intervention. And then actually at a 3-month follow-up, the control group caught up and had more or less matched the intervention group out by that point. But there was a greater decline during the actual 6-week treatment. Sleep-related impairment is a measure of daytime functioning. So it's asking about things like if you have difficulty during the day because of your sleep problems. So that would be like if you are having trouble working or studying or functioning in the daytime because of how sleepy or poorly you slept last night. So again, we see greater improvements in that in the intervention arm. These little asterisks indicate the statistical significance, and S for not statistically significant. So we didn't have the significant effects at follow-up, although the trend was there. But we do have significant effects at post. Sleep disturbance is a measure of what happens at nighttime, but it asks a little bit more about like disruptions to sleep rather than the kind of perceived symptoms of sleep. And there, it's a similar pattern, but it was not statistically significant. And then the last kind of related measure is fatigue or their energy levels. And again, we see that the intervention group decline in their fatigue symptoms. So their fatigue reduced more quickly, so they had more energy after the intervention compared to the control group. So those are sort of our main results, but we also asked them throughout the intervention to complete sleep diaries every day for 6 weeks, and also to wear the accelerometer every day for the 6 weeks of the intervention. And so these are the data there. The left column is based on the sleep diaries. So this is the self-report. Like each morning, they will fill out a questionnaire, basically, like what time did you go to bed? How long it take you to fall asleep? Did you wake up overnight? What time did you wake up in the morning? And from that, we can calculate some different measures. Maybe I'll start here at the bottom. So TST is total sleep time. It's what we call like the actual sleep duration. So it's supposed to be how many hours they're actually asleep. And we can see a couple of things here. The shaded region is the confidence intervals. And so what we see is that after the start of the intervention, so where the initial session is like right before the start of these data, because actually they start the sleep diaries after the intervention begins. I kind of wish I had done that differently, but in hindsight, I will do differently, but this is the way it was. So the first initial consultation happened here, and then we start to collect the sleep diary. And what we see is the groups are randomized, so we assume any difference has to do with the condition. Initially, they actually report on their diary, on the self-report, spending more time asleep. And then over the weeks, the control group kind of catches up. So there's a significantly more sleep self-report in the first few weeks, and then the control condition by the end had actually caught up. Another kind of two things that we look at, so WASO, awake after sleep onset, W wake, A after, S sleep onset, O, is like if they wake up at 1 a.m. for an hour, that would be counted as WASO. And this is in minutes. Here you see a small difference, but it's not statistically significant between the two groups. They both come down over time, but the intervention group is not significantly different. It's a little bit lower, but not significantly than the control group. SOL is sleep onset latency. It's how many minutes from when somebody starts trying to sleep until they actually fall asleep. And again, no difference between intervention and control. Both groups have some decline over time. And then the sleep efficiency is a ratio of the total sleep time to how long they are in bed. So this is like a percentage. If it is 100%, it means all the time they spend in bed, they're actually asleep. If it's 0, it would mean all the time they spend in bed, they were awake. And here again, we get initially in the first few weeks, significantly higher sleep efficiency than the control. Over time, control catches up some and they end up not significantly different. And then the right-hand side is all those same metrics, but this time off of the objective accelerometry data. There are the two parts that I'll just point out that we were kind of interested in. Actually, on the objective data, the two groups do not differ right after the intervention, but by the end of the intervention, sleep efficiency is actually higher in the treatment group. And for sleep duration, there is significantly higher sleep duration right at the beginning, but over time, again, they kind of converge when you look at the objective data. Okay. Just looking at the time, I might actually skip this and some of these next ones. It's in the slides that you have, so you can see. We tried to look, maybe we'll comment really briefly. We tried to look at what specifically people changed to drive some of these changes. And what we noticed in the intervention group is that they spent less time in bed awake. And that was primarily not overnight or going to sleep, but it was primarily that actually in the morning when they wake up, that they actually get out of bed rather than kind of lying in bed in the morning, like kind of dozing in and out or not quite sleeping, but also not getting out of bed. And that was one of the specific behaviors that they changed a lot. The other thing we thought was a little bit interesting was that across the 6 weeks, by the end of the 6-week period, they had actually reduced the variability in their out of bed time. So it's hard to control people's into bed time precisely because I might say go to bed at 10 p.m., but at 10 p.m., if you feel really alert and really awake, there's no point in having you get in bed. You cannot fall asleep if you don't feel sleepy, right? And I can't yell at you into sleeping quickly. But you can wake up at a particular time. So you can say, okay, get up every day at 7 a.m. Even if you're asleep, set an alarm clock, it can wake you up. So we can wake you up more easily than we can put you to sleep, right? And if you are consistent, that can help circadian rhythm, which can ultimately help you hopefully sleep better. So this out of bedtime variability, we see decrease more in the intervention group than the control group. And just because this is a methodsy group, and maybe you have some interest in this, to do this, we used a mixed effects location scale model. So I think it's a type of regression model. Usually in regression models, we do like this, right? So you have some intercept, you have some data X and some regression coefficients and the product of those two things, right? If you have like the matrices, if you multiply those, that's kind of your prediction. But that's focused on like the mean level. And a lot of times we just assume that the errors follow some normal distribution with some variance, right? Location scale models, the mean is the location, but they also model the scale. So rather than assuming that everybody has the residuals always follow the same normal distribution with a mean 0 conditioned on your predictors and some variance, we basically fit some sort of regression model, typically to the log of the variance, because variances are bounded by 0, but if you log transform, then it can be negative or positive. And so that's like a pretty standard location scale model. And so that's how we modeled the effects of the out of bedtime variability is we just have that each day. And then we predict the variance, essentially the residual variance in the out of bedtime with this model. Okay. We have just finished a second trial, which we're starting to get results from, but maybe for now, actually, I just skip this because of time. I want to spend some more time on the multi-level coda, and I think I only have a few more minutes. Very happy to talk about that other trial, though. So I told you in the first application of coda, we only use like the single level model. So even when we have the daily data, we kind of ignore that and just average all of them. And that's not really ideal. It loses a lot of data. It's impossible to look at kind of daily changes, right? And also, as we talk about these sleep interventions, I haven't actually applied these compositional analysis to them, but we really want to. But we have data over multiple days, and we think in the context of an intervention, people's sleep and the activity composition is probably changing from day to day, hopefully as they apply the strategies they learn in the intervention. So we really needed some way to actually apply something like these compositional data analysis to repeated measures. And so we started to work on that over the last few years. There's, at least when we started this, we don't find many software tools to implement these things. And so it's possible to create the models, but it takes maybe some more work. So we started to actually try to work this out and build the tools. So this was again led by my PhD student, Flora. She's very smart and graduated now. You should have her talk sometime maybe, because this is a lot of her work, but now I guess you have heard it anyway. So we published this paper this year on Bayesian multi-level compositional data analysis. And so it extending CODA into the multi-level context and then using these Bayesian models to actually do it. And we introduced the method as well as did a simulation study to evaluate its performance.
Mm-hmm.
So the basics, pretty similar to what we had before. So we have some X vector, right, which is some D part composition. That part doesn't change in CODA.
Mm-hmm.
Now we have to have do more subscripts, I guess, because we need to be able to account for not only the different participants or observation, but also participants. So, for example, the ith observation in a longitudinal study of the jth person. Of course, you can have other multi-level structures, right? So you can have children nested within schools or patients within hospitals or other nesting structures, right? Perhaps the most interesting part of this, beyond sort of the coda, is that we have interest in what we call disaggregating the levels. So when you talk about people, you might think about how long does somebody sleep on average, and then how different is today from their usual average. So for example, if I sleep 7 hours usually, but then today I sleep 8 hours, I'm sleeping 1 more hour than normal, right? If I normally sleep 9 hours and today I sleep 8 hours, I'm sleeping 1 less hour than usual. And it's kind of useful to do this because in these longitudinal studies, we often are interested in what's happening today that's different from what's sort of happening usually. So we don't want to conflate stable differences between people with these kind of daily fluctuations. And so in the compositional space, you can take that compositional data and basically decompose those two compositions. You can think about them as a product. You have the between-person composition and the within-person composition, the daily fluctuations, and the product of those two actually is what gives rise to the specific composition on any given day. And we denote that with like these superscript B and W for each of these components. And so then you have this between composition XB, and that doesn't vary from observation to observation. It only varies by person. Each person has their own average, essentially. And then you have a within composition, which varies between people and between days. And together, if you take the Kronecker product of those two vectors, right, then you get the overall composition that we actually observe daily. And each of those things, XB and XW, are themselves compositions. They have different constants, but they are both themselves compositions. And so once we do that, we can apply the same ILR transformation that I talked to you about earlier, but now to these kind of between and within person composition. And then we have some coordinates that we are able to use fairly standard multi-level models with. So this is kind of our like a basic model, outcome distributed, this kind of compositional transformation of the inverse of a prediction and some other parameter. And then we assume that the predicted value is basically the data times whatever regression coefficients plus any random effects, which the Z matrix would be kind of for individual participants, and mu like the random effects there. And we can allow like random slopes. So we can allow these co-regression coefficients, of course, to differ for different participants. Okay. So we set this up. We worked this out. We ran a simulation study just to evaluate the performance of these things and whether it actually gives back, whether the results we can recover from the parameter estimates, what the true values are. And what is shown here in this table is the estimates for different parts. I'll draw your attention just to a couple of pieces. One is the bias. So is there on average any bias in the multi-level models? Or in the compositional substitution analyses we call when we actually predict those values for one composition, generate predictions under a different composition, take the difference, does that recover the truth from the simulation? And on average, both of those are unbiased with quite narrow ranges. Coverage is whether the 95% credible intervals from the models actually cover 95% of the simulated results. And indeed they did. So the coverage is really good. Some of these other results here have to do with Bayesian analyses, the effective sample size, divergent transitions, things like that, which I can talk about perhaps in the questions later if there's interest. So in short, the method seems to work conceptually. Simulation studies confirm it works well. We have implemented it into an R package. that is publicly available now. And the package paper also, a paper introducing the software has been published in multivariate behavioral research now. So that's all freely out there. And then I want to just very quickly here in the last minute or two, go over just an application of this. And so we repeat those analyses I showed you at the start when we introduced CODA, but now we are smarter and we have more tools to be a little better than we were before. So now we can actually utilize the daily data rather than just average over all of that variation from one day to another. Okay. And so these are similar things, similar graphs to what I showed you in the last composition, but here on the panel A, we're looking at that high arousal positive affect. So that's like the cheerfulness, happiness sorts of things. But this is at the within person level. And here what we saw is actually a little bit different results from when we analyzed this on average. So we find that on days when people spend more time in the light activity at the expense of sleep, especially when it's at the expense of being awake at night, a little bit if it's at the expense of sedentary behavior, and not significant if it's at the expense of MVPA, that they have the higher arousal positive affect. And so they're able to actually start seeing the differences across this, where like the light activity increases high arousal positive affect, but only when you are substituting sleep, awake, or sedentary behavior. When you substitute it for MVPA, it does not make a difference to your affect. It's not significant. And the strongest effects is actually when you spend more time in light activity by sacrificing like a time awake in bed or time awake at night. That is sort of the best substitution on a daily basis to maximize the positive affect. At the within person level, so on a daily basis as well, we see that when people spend more time in moderate to vigorous activity at the expense of sedentary behavior, then they end up with less low arousal negative affect, which basically is things like a feeling sad or guilty or depressed. And so that's reduced on days when they have more time in MVPA, but only substituted for the sedentary behavior. Similar pattern, but not statistically significant when the MVPA, when they spend more time MVPA, but they are replacing like a sleep or light activity. So, yeah, I don't have to kind of spend more time on these results, but I guess it starts to illustrate, I think, what I was mentioning earlier, that it's interesting to look at when you increase time in one behavior, what were you giving up? What time did you sacrifice to make that time for this behavior that you spend on? We also apply this to sleep architecture, which is pretty interesting, I think, but I think I have not managed my time very well, so I'm not going to go over that so I don't make you late. But you can see it in the slides, and I'm happy to take questions. Some next steps that we're hoping to do. So we hope to apply these kind of methods to the cancer intervention data. I have been doing these two lines of research kind of separately, but with a goal to eventually bring them together. And now I think we finally have the methods all figured out, and we're kind of ready to start apply to the intervention. And over time, I hope that we may not only be able to analyze the data from the interventions, but perhaps to think about how we maybe make the recommendations to people, and whether we can give more targeted recommendations based on their whole 24-hour day rather than kind of only considering one part at a time. Another thing that's a little bit interesting that Floor has recently implemented, we call it like the circadian composition. Essentially, it's multiple compositions. And so you can think about a 24-hour day, and you can separate it into, based on your circadian rhythm, what period of that day would you optimally be asleep in? And are you asleep or awake in that period? What period of the day are you optimally awake in? And what is your physical activity like during that? So it kind of takes the 24-hour day and makes it like two periods, the circadian optimal sleep window and the circadian optimal wake window. And within both of those kind of fixed periods, we can calculate the composition of your actual behaviors. It's a fairly straightforward extension, but we have done that and implemented it in the software. I'm not sure if the software is quite public, but if it's not, it will be very soon. Some challenges with compositional data is addressing missing data and zero data. So that doesn't always happen. And with things like the components that I'm showing you right now, it's not too much issue. But when we start to look at like sleep architecture or other things like that, depend on what you have. If anybody has zero of that, or even for MVPA, if somebody has 0 minutes in MVPA on a given day, because of the log ratios, you cannot take a ratio with zero. So it creates some kind of mathematical problems. There are some ways to deal with that, but it's a little bit more challenging. And then also kind of future directions. We have been measuring sleep off the accelerometry, and that's okay, but it's a little bit indirect measure of sleep. We have a little bit of data using EEG at home to measure sleep. And I think kind of ultimately, I hope to be able to combine wearables so that we measure the like physical activity from accelerometer, heart rate, things like that, but we measure the sleep with EEG, which gives, I think, a more precise estimate. And so with that, I will say thank you very much. I'm very happy for questions, comments. I'm very happy to take collaborations. Any data that we have, I'm very, very comfortable to share or to brainstorm methods or ideas with you. I think there's a lot of very bright people here. So if you have the suggestions on what we should be doing or different techniques or ways to do it better, always love to hear.
Yeah. Thank you very much, Joshua. So, yeah. Wow. So more equation than I expected. So yeah, great, great, great. So, any questions? So please, unmute yourself and, feel free to ask a question to Joshua, or you can also suggest some idea as well, regarding the question he suggested the last slide. Who want to go first?
Oh, can I have a question?
Yeah, sure. Let me stop the recording.